Before beginning the main content for this video, I wanted to give a short introduction covering two topics. Firstly, I am experimenting with using AI text-to-voice to create the audio recordings for this channel. I am hoping this will reduce the time it takes for me to produce a video, and this is, after all, a channel dedicated to AI workflows. For this video, I have used 11 Labs text-to-speech, mainly the 11v3 model, but I did create a small amount using the 11 multilingual v2 model. Even for a relatively short video such as this one, I needed to sign up for the $5 US starter plan to have enough credits to create the voiceover for the full script. Secondly, the content of this video is now over 2 months old. I was partway through creating this video, late January 2026, when I had to pause to focus on other priorities. This is why I am talking about Codex 5.2 and Opus 4.5 in this video. I considered scrapping this video, but I decided to release it for continuity as the feature developed in this video will form a permanent part of the application. Future videos will return to using the latest Codex and Claude Code offerings. I haven't decided what the next feature development will be yet, but there is a very strong chance it will be integrating AIS or changing the symbology to look more like Flight Radar 24 or OpenSky's flight map. Anyway, on to the normal content.
Hello, and welcome to the video. Today's video will be covering the first in what will probably be a series of comparisons of Claude Code and Codex making updates to the Flight Tracker application. For those of you new to the channel, I've been using Codex to implement what has turned into a Flight Tracker style application, similar to Flight Radar 24. I've been using Codex solely up until this point, and I've been quite impressed with Codex's performance, but I do want to see how other coding agents perform, hence the introduction of Claude Code. The first comparison I will be covering is a relatively simple change request. I ask GPT 5.2, Codex, and Claude Code Opus 4.5 to create an overlay showing the OpenSky Network bounding box on the map when the application is obtaining live ADS-B data from OpenSky Network. You can see the finished product running on the screen now. I think I've covered this in a previous video, but to recap, OpenSky Network exposes a free API that publishes ADS-B data. That is, if I'm not mistaken, mainly collected by volunteers around the world. When requesting data from the API, I specify a relatively small geographic area I am interested in.
I do this because I currently access OpenSky's data as an anonymous user, and there are usage restrictions for anonymous users. Requesting data for a smaller geographic area reduces the usage credits consumed by each request. On the screen is the prompt that I supplied to both Claude and Codex. Also displayed is a mermaid diagram of the application's architecture that Codex created for me late November 2025. I'll run through the architecture to give viewers some context for terms I might use later in this video or in subsequent videos, and then I'll run through the prompt I gave to Claude Code and Codex. This architecture diagram shows the three main components when the application is in OpenSky Network mode, consuming live data from OpenSky's REST API. The small box on the left represents OpenSky itself and is, of course, external to the application. The box in the middle represents the application's track service component. The track service is a Fastify-based fusion engine that serves as the authoritative source of aircraft track state for the aircraft visualization. In OpenSky mode, it polls the OpenSky Network REST API every 5 seconds for ADS-B state vectors within a configured geographic bounding box, receiving raw aircraft positions, velocities, and altitudes in metric units. The TrackStore class ingests these samples, converts them to aviation units, feet, knots, FPM, applies exponential smoothing to heading and ground speed to reduce jitter, maintains a 60-second position trail history per aircraft, and coasts out stale tracks after 30 seconds without updates. The difference broadcaster then computes differential frames at 10 Hz, containing only added, updated, or removed tracks, and broadcasts these track difference frame messages over WebSocket to all connected web clients. Key dependencies for the track service include Fastify, Pinot for structured logging, and Zod for configuration validation. On the right-hand side is the web client. The web client is a React 18 single-page application built with Vite that renders the real-time aircraft track visualization in the browser. It connects to the track service via WebSocket and receives track difference frame messages at 10 Hz, which it merges into a ZooStand store that maintains normalized track entities containing both current and previous states for each aircraft. MapView is the primary visualization component that renders the interactive aircraft display. It initializes a map Libra GL map with tiles fetched from the track service and overlays airspace boundaries. Using DeckGL's Mapbox overlay, it renders multiple WebGL layers, a layer for aircraft position symbols, a layer for historical trails, a layer for text like call sign, altitude, and speed labels. MapView reads track state from ZooStand. It handles click and hover events to update selection state, supports follow mode that auto-centers on a tracked aircraft, and displays hover tooltips with track details. Track Sidebar is a sidebar panel for searching, pinning, and inspecting aircraft. The top section contains a search input. The middle section displays a list of watched tracks, displaying call sign, flight level, coordinates, and ground speed for each. Each row offers buttons to center the map on that track, toggle follow mode, or remove it from the watch list. The bottom section shows detailed telemetry for the currently selected track, altitude, heading, vertical rate, position, timestamp, and aggregate statistics, total tracks, and tracks visible on map. The status overlay is a compact overlay positioned on the map that displays the current data source mode and connection health. This gives operators immediate visual feedback that the data feed is active without cluttering the main visualization. The prompt is fairly basic. I ask for an addition to the web client that shows the OpenSky bounding box to the user when the application is obtaining data from OpenSky Network. The bounding box is the geographic region the application specifies to OpenSky when it is requesting aircraft data. When the bounding box is displayed to the user, it should be filled but still transparent. I used Claude first, so let's run through its performance first. As you can see, Claude is relatively verbose, reporting what it is doing as it plans. It tells us that it is entering plan mode and that it needs to explore the code base to understand the application so it can propose a change. I think it is worth noting that, as far as I can tell, Claude Code does not perform codebase indexing. Claude takes about 1 minute to read the parts of the codebase that it thinks are relevant. It then moves on to planning the change, which takes just under 2 minutes. The plan is quite detailed. Claude Code proposes modifying 2 files to implement the change, which I ended up deciding wasn't necessary. As part of the plan, Claude Code provides some pointers on verifying the change. I didn't ask for verification steps, but I did appreciate Claude Code providing them. Eventually, I get around to approving the plan and asking Claude Code to execute the implementation. Claude Code takes about 2 minutes to complete the implementation. As you can see, the communication from Claude Code during the implementation is very good, progressively ticking items off a checklist of tasks. Interestingly, it included running the linter. I didn't ask for that, and I hadn't specified in Claude.md or agents.md that running the linter was a requirement after every change. Claude Code seems to have independently decided it was a good idea, which I agree with. And as it turns out, there were linter warnings produced in the code change. Claude Code addressed the linter warnings immediately without any intervention from me. As I say, the implementation took about 2 minutes, and the planning took about 3 minutes, so all up, Claude Code took around 5 minutes to make the change, which consisted of modifying 2 files, adding 38 lines, and removing 2 lines of code. I'll return to the actual code change later on, when I compare the change Claude made to the change Codex made. Claude Code's change worked well, and I didn't see any issues.
Next, I asked Codex to make the same change. While Codex does display what it is up to during its planning, I didn't find it as easy to follow as Claude's updates. Codex finished planning in about 40 seconds, much quicker than the 3 minutes Claude takes to plan. However, for some reason, Codex doesn't display the plan to me. I have to ask to see the plan, which Codex displays immediately, which suggests to me that the plan was really made, just not displayed. That was a bit of a fail for Codex, as the prompt asks for a plan that I can review and approve. Codex even tells me after it has finished planning that it will wait for me to approve the plan before implementing.
The plan seemed reasonable, so I asked Codex to implement, and to include instructions on verifying the change as it suggests in its plan. Codex takes 18 seconds to implement the change and provide the verification instructions. Codex provides an adequate description of the change it made and, as instructed, provides manual verification instructions. As with Claude Code, the change worked well on the first attempt. So, Codex successfully completed the change request in just under a minute, while Claude Code took around 5 minutes. But how did the code changes compare? Claude made changes to 2 files, while Codex modified a single file. Claude and Codex both modified a file called mapview.tsx, which is part of the web client, and the second file that Claude modified was called symbology.ts, also part of the web client. On the screen is the mapview.tsx diff for Claude Code's change on the left and Codex's change on the right. You can see that the changes are quite similar, which is encouraging. They both add a new polygon to represent the OpenSky Network bounding box, and this polygon is added to the layers displayed over the base map. If the application is not running in OpenSky mode, the new layer is nulled out, so no bounding box will be displayed. There are some differences to note though. Firstly, when deciding if a polygon has to be created, Claude Code and Codex both check if the data source is OpenSky. No issues there. But Claude Code also checks if the OpenSky region of interest bounding box exists. Codex doesn't do this, and it is unnecessary as region and bounds are not optional. I asked Claude Code about this, and it agreed that the check was unnecessary. Secondly, Claude Code decided to create a new accessor function, bounds to polygon, to return the polygon's coordinates, and implementing this new function was the change to symbology.ts. Codex simply defined the polygon's coordinates in mapview.tsx. I couldn't see a compelling reason for the added complexity of Claude's implementation. I asked Claude about this design decision as well, and Claude said for this simple use case, there was no compelling reason to use the accessor function. In any case, both implementations worked, but in the end, I decided to use Codex's change, mainly because it was leaner and I didn't see the need for the extras Claude included. Having said that, I'm sure it would have been quick to get Claude to remove the redundant check and the unnecessary accessor function. I was quite impressed with the speed of Codex's change. It made about 40 lines of change in under a minute. There is no way a human of any experience is doing that. Adding several minutes for a human to review Codex's change and ignoring the QA you'd have to do in any case, you could be ready to commit Codex's change in 5 minutes. A very experienced or exceptionally talented human with knowledge of the code base and the relevant libraries might also work that fast. An inexperienced developer could take hours. Claude Code was slower, taking 5 minutes. As before, after adding several minutes for a human to review Claude Code's change, this change could be ready to commit in 10 minutes. This would still be pretty quick for a lot of human developers. As noted above, this could be much, much quicker than an inexperienced human developer. I think using AI in this case would almost certainly be a productivity improvement over a human doing the change independently. I think it is worth remembering that in one respect, Codex and Claude Code can be considered inexperienced developers. This is because for each new chat, they have to relearn the application's codebase. There is some context in Agents MD and Claude MD, but they need to reread the source code every time I get them to make a new change.